Hi everyone, my name is Stephen Weigel, and today we're going to talk about the connection between LS notation from 21st century microtonal music theory and prime form from your older, now mainstream post-tonal theory, JK LOL. These videos document the connections I've discovered between the two. The point of the next two videos is to discover the way to change an LS set to prime form. This will also work for LMS, LM, little ms, blah blah blah, any number of step sizes. For brevity, I'm calling any collection of L's and S's and M's, etc. a scalar class set. Scalar class set is a great name because it's not a term for anything else widely used in mathematics yet, couldn't even find it in Google, and it's analogous to pitch class sets. Yeah, sort of. These scalar class sets are useful as more thorough categorizers. In fact, I even redid Fort's table of pitch class sets with LS involved. I dare you to out-nerd that one. Let's start with understanding a basic kind of permutation, which will help with understanding the easiest part of this problem. Forget music theory for a second and take a nice deep breath. Okay. Let's say we have a three-letter word, and the only letters we want to put in the word are A, B, and C. Okay, then that's not too hard, right? We have 3 letters for the first one, and 3 for the second, and 3 for the third. So we have 27 different words. Alright, that's all fine and good. We could just use x to the n, and n would describe how many letters there are in the word, and x just describes how many letters are available. Now, what if we get a little stricter? Let's say we still want a 3-letter word with A, B, and C, but we want to use each letter only once, so one A, one B, and one C. Well, let's try making one of the words and see what that tells us about the other possibilities. We'll start with B here, and we know there's 3 letters we can use. Alright, now the second letter. We can't use B again, but we could use A or C, which is 2 letters. I pick C because why not? And then the last letter can only be A. So that's 1 letter. We have now described the factorial, which is a really important operation in combinatorics. An exclamation point in a factorial tells you to multiply that number, then itself minus 1, itself minus 2, etc. until you get to 1. By the way, 0 factorial is 1 because an empty set can only exist in one way, but that doesn't really matter. These factorials can be used with any scalar class set easily to describe the number of ways any number of L's, M's, and S's can be written out. This is called the number of permutations of a scalar class set. The total number of L's, M's, and S's, which I call number of tones, is at the top as a factorial, and each subsequent number of each term is a factorial at the bottom. This is the act of dividing out repetitions. It's like 5L2S is a 7-letter or 7-tone word, and we can divide out the 5 and the 2 because those letters are the same. We're getting rid of redundancy. Also, another fun note, L and S can be any size or switch places among the coefficients. 5L2S and 2L5S have exactly the same permutations, normal orders, and prime forms. It's the coefficients that's important. Then, to get normal orders, we just need to divide by the number of notes again. Because think about it, if I have a 7-letter word and I divide by 7, don't I get rid of all the cycles of that word? Why, yes! I don't need to cycle each word 7 times to see all 7 of its modes when getting the normal order. The normal order is really efficient with this. See, the 3 normal orders of 5L2S are just the major scale, Neapolitan major, and the melodic minor scale ascending. Hooray, we did it! However, there is one instance in which this equation won't work right away, and this is when we have transpositional symmetry! In music theory, especially post-tonal theory, transpositional symmetry is what happens when you cycle a scale and then you get the same thing again. For example, when I cycle the diatonic scale here, 5L2S, I don't ever get the same mode twice. But when I cycle the octatonic scale, 4L4S, whoa, I do get modes that are the same. Transpositional symmetry alert! Scalar class sets are only transpositionally symmetrical if they all share a common factor. Besides 1, of course. 4L, 4S shares a factor of 4, which means that if you split the word into 4 equal parts, there's a little repeating scalar class set inside it. See? It's 1L, 1S. 1L, 1S is also 4L, 4S with its coefficients divided by 4, and that's the reason why. This is no coincidence. The method to go from scalar class set to prime form now changes a little if you have transpositional symmetry. Watch carefully. We'll use 4L2S as an example. If the coefficients have a factor in common, you divide by that factor to find the nested scalar class set. Then we find the number of permutations for scalar class sets, the original and the nested. We know that the number of permutations of the nested set is equal to the number of permutations that are affected by transpositional symmetry. So now, we subtract the number of permutations affected from the number of permutations total. Once we split the permutations into these two groups, affected and unaffected by transpositional symmetry, we can then divide each by the number of tones according to the two sets. See how the unaffected permutations divide by 6 now, and the affected permutations divide by 3. 6 tones are in the original set and 2 tones are in the nested set. It's also helpful to look at this by listing the number of normal orders multiplied by their respective numbers of tones for the original and nested set. In sets with more than one factor in common, the process has to be repeated again for doubly nested sets, so that every set that can incur a subtraction or have factors in common gets a subtraction. This is why I didn't do 4L, 4S first. It can divide by 4 and 2, you see, which makes it a little bit more complicated. I won't go over this in detail, but this doodling should give you the idea with a few examples. And that's all you need to know about scalar class sets to normal orders. Next up, the elusive prime form.